Now we're going to take a look at the signs that we would get for the flux and for the EMF. You can follow along. There's a blank copy of this handout. If you go to my course folder on the M drive and then to the electromagnetic induction course folder, there's a blank copy of this in that folder. It is called Signs for EMF. Okay, so the flux is equal to the integral of B dotted with dA, but provided that we have a uniform magnetic field, we can pull the B outside and then just integrate, and that will give us B dotted with A. So we have uniform magnetic fields here, and so the flux is equal to B dot dA. Okay, now you are free to choose your coordinate system. So for these four situations that we have here, we are going to see what happens if you choose the coordinate system so that B dotted with A is positive. That means choosing the direction for the area vector so that's pointing in the same direction as your magnetic field vector. So if the magnetic field is pointing into the page, we're going to say the area vector is also pointing into the page. And if the magnetic field is pointing out of the page, we're going to say the area vector is also pointing out of the page. So you're choosing the direction that the area vector is pointing in. And remember, you're free to do this. If you have a loop, the area vector has to be perpendicular to the plane of the loop, but that could be pointing out of the page or pointing into the page. And you're free to choose which one it is. Remember that for Gauss's law, we had a closed surface. So if the surface is closed, the area vector would be pointing away from the inside of the surface. But for a loop like this, you have to choose the positive direction. So we're going to look at what happens for all the different possibilities. Okay, so the first two situations that we have here, the magnetic field's pointing into the page, but in this case, the magnetic field is increasing, and in this case, the magnetic field is decreasing. So we're going to look at what happens in both of these situations, and we're choosing the positive direction for the area vector to be pointing into the page. Now, if the magnetic field is increasing, then you would induce a magnetic field which is pointing in the opposite direction. So the induced magnetic field would point out of the page and your current would go this way. Okay, now let's take a look at the table that we have here. The flux is equal to B dotted with A, but I chose A to be pointing in the same direction as the vector B, so it should be positive based on how I chose the direction of the area vector. That's true for this case, and it's also true for this case. So because we chose the area vector to be pointing in the same direction as the magnetic field, when we dot B and A, we get something positive because those vectors are pointing in the same direction. If you look at the last two situations in the handout, if you define A to be pointing out of the page, that changes what you have in the table here. So if the area vector is pointing out of the page, that's the opposite direction of the magnetic field vector. So when you do the dot product here, because B and A are pointing in the opposite directions, you get a negative sign. Now let's go back to the first two situations that we have. If the magnetic field is increasing, then the flux is increasing. So the flux is positive and increasing. And so if you take the derivative of the flux with respect to time, you get something positive. Here, the flux is positive but decreasing. So if you do a graph of flux with respect to time, if the flux is decreasing, you'd have a negative slope. So the derivative is negative. I put this step in the table just to help us to go to the EMF, because remember, for the EMF there's a negative sign in front, so rather than trying to do all of that in our heads, if we already have the derivative here, then when you do the EMF you just change the sign. So this was positive, so now you just change the sign and it's negative. This is negative, so now you change the sign and it's positive. For the last step, we get a sign for the current, and that comes from using Ohm's law. So the EMF is equal to the current times R, and the R is just the resistance of the resistor, and so the EMF and the current should have the same sign. So current would be negative here and positive here. Now we have to figure out, what does a negative current mean and what does a positive current mean? Well, those signs are related to how you chose the direction of the area vector. So if the current is positive, that means if you put your thumb in the positive direction, and that was the positive direction that we chose for the area vector, so we said the area vector was pointing into the page, so the positive direction for the area vector is pointing into the page. So if you put your thumb in the positive direction, the current's going this way, which is, I think, what we figured out before when we said when B is decreasing, the magnetic field would be pointing, the induced magnetic field would be pointing in the same direction as the magnetic field we already had, so the current would be going that way. I'm not sure if we actually said that before, but there we have it. It agrees with what we have there. Okay, we did test this using Lenz's law to say that the induced current would be going this way. And we have a negative sign here. For my area vector, I said positive was in the same direction as the magnetic field, which is into the page. So if the current's going in the negative direction, that's the opposite direction of the area vector, because it's negative and this is positive, which means you put your thumb pointing out of the page, because we said positive was into the page for the area vector. So we get current going that way. So that's how you get the signs from using Faraday's law instead of using Lenz's law. Okay, and then we have these two situations here. We are still going to define A so that B dotted with A is positive, which means we have to define the area vector so that it's pointed in the same direction as the magnetic field. So now the positive direction for the area vector is pointing out of the page. So that's going to give us the coordinate system that we use to figure out the direction of the current. Okay, so the flux must be positive because that's how I defined the area vector, so that the flux would be positive. And if the if the magnetic field is increasing, the flux is increasing, it's positive and increasing. So if you would do a graph of flux versus time, you would have a positive slope. Here the flux is positive but decreasing. So if you do a graph of flux versus time, you'd have a negative slope. So the derivative is negative. Then for the EMF, you just change the sign based on the equation here. So we change the sign. And then based on Ohm's law, the EMF has the same sign as the current. So here the current is negative. That means I have put my thumb in the negative direction, which is into the page based on the coordinate system that I use for the area vector, and the current flows this way. Here the current's positive, so I put my thumb in the positive direction, which is how I defined my area vector, and the current flows this way. And then let's just check to make sure that that agrees with what we would get using Lenz's law, which says nature abhors a change in flux. So here the magnetic field is increasing. If the magnetic field is increasing, I would induce a magnetic field in the opposite direction, and I would get current flowing this way. Here the magnetic field is decreasing, so I would induce a current in a magnetic field in the same direction, and I get current flowing this way. Okay, then finally, we would look at what happens if you just always define the positive direction for the area vector to be pointing out of the page, which I think makes sense to do. But for these situations here, nothing would change because the positive direction was already pointing out of the page. Okay, so the only thing that would be different would be these two situations here. We already looked at the direction of the flux and said it would be opposite because now the positive direction for the area is pointing in the opposite direction of what it was in our situations up there. And here the flux is negative and the magnetic field is increasing, which means the flux is getting more and more negative. So if you draw a graph of that, the flux is negative, the absolute value of the flux is getting larger, and the slope of this is negative. Here the flux is negative to begin with, but the magnetic field is decreasing, so the flux is getting closer to zero, which means you have a positive slope here. Then you change the sign for the EMF, and the current has the same sign. So the current here is flowing in the positive direction, which means if I stick my thumb in the positive direction, and here we said the positive direction was going to be pointing out of the page, that gives me the direction of the current. And here the current's negative, so I put my thumb in the negative direction, which is into the page, and I get this for the direction of the current. Now, if you compare that to what we had at the top of the page, you'll see that the current's flowing in the same direction in both situations. It's just a matter of what sign you get for this. Here the current's flowing in the same direction, but we said this was positive current and this was negative current. So that's just based on how you define the positive direction, and you're free to choose the area vector to point in either direction, either into the page or out of the page, but that's like setting your coordinate system, and then the sign for the current depends on how you set that coordinate system. Okay, so as long as you keep track of all of that, you can do it whatever way you want, and we'll see how that works when we do some example problems.